Very excited to be here. As the title of my presentation suggests, I'm going to be a little critical of my own field. So let's begin. OK, actually, before I begin, this work is based off of 3 previous ones, 1 video that he was just describing, and 2 blog posts I made subsequently where I realized that I needed to elaborate on that. So let's get started. To begin with, I'm going to talk about what fuzzing is and why it's so dang effective. So to start with a little history, let's begin with the classical era, which is pipe dev view random, as I like to describe it, where we start out with our protagonist, Dr. Barton Miller, who is sitting in his home, connecting out to his office, where he's trying to basically interface with a terminal over a dial-up connection, pre-error correction codes. And what ends up happening is, as he's typing, a storm outside disrupts the actual content of his keystrokes, leading to some corruption of the input and subsequently crashing the actual application, which was surprising at the time. So in order to continue this investigation, he inflicted it upon his students by making a project where they were required to create what he called the Fuzz generator. And this is in fall of 1988. And the idea was generally to test programs by giving them an unpredictable input stream. And turns out this works pretty dang well. So in 1990, they could crash from 1/4 to 1/3 of all Unix utility programs just by throwing random data into them. In 1995, they did it again. They could do 40% of Unix utilities and 40% of X-Window applications, which is insane. And their general conclusion was that it would be irresistible to corporate testing groups. I suppose that's why I'm here today. Anyway, so fuzzing actually starts before Barton Miller coined the term. Back in 1971, we had the first paper published about using random testing in order to qualify certain designs, which was then extended in 1975, and then so on and so forth. It became more popular. And then 1990, 1995 were the studies I just described from Barton Miller. And it turns out this still works to this day. Trilobits, which is a company that is quite prominent in security testing, basically did the same experiments that they did back in 1989 and found, yeah, most of these utilities still crash. Not optimal. And we even see some testing systems that still use this as a general process for testing to this day, and they work very well. OK, that brings us to the Renaissance, right? This brings us to AFL, for those of you who know them. And in order to describe what is happening here, let me give you an example. Given this program, right, how many guesses do we need to make in order to cause this program to crash? On average, about 2 to the 31 guesses, right, which is not optimal. So the question is, can we use the code, which clearly here, right, it's somewhat obvious how this program should crash. Can we use the code itself to inform us how we should actually be testing it? And the answer is yes. So suppose we take each condition in this program, right? And this is simplifying a bit, but suppose that we take each condition in this program and we assign a variable to it that represents whether or not it's been hit and the condition has been satisfied, right? And now what we can do is we can basically make an array in which each one of these conditions is labeled as so. So you can see I've added a little supertext there. And now what we can do is we can basically treat the program as a function which takes inputs and turns them into information about which conditions in the program were satisfied. So you can see here, I have ADF EC3. A condition is satisfied, so I set it to 1, right? Similarly, if I then change this input, say by changing that D into a B, right? Now, my function will have A succeed, it will have B succeed, so I have this mapping between inputs and the coverage of a program, right? Coverage being the classic term for this. Okay, and here is how most coverage-guided fuzzers to this day work, is that you have a corpus of inputs, right? Basically a set of inputs that you know to do something interesting, and then you can map that corpus into a global coverage map, right? Basically, if you take the union of all of the coverage that we've ever observed over all of those inputs, that gives us the global coverage map. And so now, what we can do in order to continue our testing is, we take some input from that corpus, we schedule that input, we then mutate that input, we run it, and we can see that we've changed our coverage map here. And now we check if there are any new changes in the global coverage map that would have successfully been taken in as a result of adding this input to the corpus. And in this case, we do see that 0 changes to a 1. Therefore, we add it to the corpus, and we continue testing. This is the basis for a majority of modern coverage-guided fuzzers. So what this really does for us is something rather interesting. It allows us to use mutation to take existing inputs that we know to be effective and make new inputs, which means we can explore the program, and we can use the coverage to tell us which inputs we need to take in the future to mutate further, right? And this works really well, like really, really well. And I have a lot of little asterisks here, but fuzz testing has discovered the most bugs of any testing strategy, probably, right, after the fact. Anyway, don't worry about it. It works really well. And now that brings us to our third movement, right? We've had coverage guidance for some time now. As of 2014, this was introduced to the public. And in modern fuzzing, we have a lot more strategies than we had available to us in the past. I'm not going to go over them in detail, but effectively they boil down to 3 general questions, right? First one being, how do I provide input to my target, right? Seems like an easy question to answer, but what does it mean to fuzz a hypervisor, right? What does it mean to test a CPU, right? These are very difficult questions to answer in practice. The second one, how do we know which inputs to run? If we have a particularly expensive target, it might be prohibitively expensive to actually run that target over and over again, like we would if we were testing, say, an image parser. And then finally, how do we know what we've not yet tested, right? How do we know that we've not found the solution yet? I love speedrunning. It's a good example of this. I don't think anyone successfully fuzzed Super Mario 64, actually. Maybe a good topic for a master's student. All right, if you want to learn more, I highly recommend this book, the Fuzzing book, in which they describe a pretty hefty majority of these strategies, and it's a great way to get started as they help you build it from scratch. Okay, so now that I've introduced fuzzing and hyped it up a bit, let's talk about the bad parts. Right? So in order to do this, I'm going to give you a selection of situations where fuzzing will tragically fail if you just try to use it off the shelf without any further thought. So the first case I'm going to describe is what I like to call reinterpretation. Okay, so let's begin. Taking my source code from earlier, I'm now going to add a little bit of code ahead of it, which looks like this. Now, I recognize this is kind of painful to read, so let's walk through how this input would actually be interpreted. What ends up happening is that the first byte is going to be used as an offset, right, to compute where to start reading the input from when we start inspecting it via these if statements. So that first one, right, I have that first byte represent my offset, and then the rest of the one will be used as the length. So I compute my offset as the offset modulo the length, because I can't go too far into the input, right? And then I end up with 0, so that tells me to start reading from the beginning of this sequence, and then that tells me my data is ABC, blah, 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 and that gives me a coverage map of this. So we're only one character away from being able to solve all of these conditions and then crashing the program, right? So let's just insert that character. let's insert a D into the correct position to see if it works correctly. So now I've added that character in. I now have 7 bytes instead of 6 bytes. So now my offset computation changes because I have 120 modulo 7, and I end up with an offset of 1. That takes me to the beginning at B instead of A, which means that now my input looks like this, and now I pass none of the conditions. And this is really bad, right? What ends up happening in practice is I actually wrote a little program to see how frequently this would change the result of a particular operation using off-the-shelf mutation tools. So I took 10 million inputs, and then I mutated them, each with libafl havoc, which is a classic mutation algorithm. And then what I ended up with was 83.5% of the inputs no longer represented the same shape that they originally did. What that means is that if I had almost solved that, 83.5% of the time, I would have completely corrupted the input. Not great. This mutation means that we've completely reinterpreted the same bytes. So originally, their meaning was something completely different, right? OK. And this obviously seems contrived, but it isn't, right? When I was testing the regex engine for Rust, what I found is that in their harness, copyright pending, we see that there's actually a situation where they pull the first byte, use it as an offset, and then use modulo length. So 83.5% of the time, if they were using libafl havoc, they would have completely corrupted the input and completely changed the meaning of that test. And this has pretty severe effects in practice beyond just the initial parsing of the input, right? Most programs look like 3 general stages. You have some parsing stage where you try to figure out what the input even means. You have a validation stage where you check that everything about the input is correct. And then you do some business logic associated with that input. If I have an input which basically starts out here, goes to the parse stage, and then, now it looks like this kind of input to the validation stage, and then we end up with some result after the business logic. A minor perturbation in the input can lead to rejection in the parsing stage. It can lead to rejection in the validation stage. It can lead to rejection in the business logic stage. Or it can lead to an entirely different behavior despite a minor perturbation of the original input. And modern fuzzing strategies try to solve this by basically bypassing each component to test each layer individually. But that only does so much, right? If I'm mutating a flat buffer, like we normally are in fuzzing, what we end up with is this parse problem. If I use a grammar and then I mutate the grammar, we end up with a validation problem. And then if I somehow were to magically spawn a semantically correct input all the time, I would still observe these variations in the business logic of the program. And the real takeaway from here is that off-the-shelf mutations just can't preserve input semantics very well. And this is important for us because if we're using coverage guidance, we basically expect that a mutation will lead to a small perturbation in the coverage of the program, right? Otherwise, it wouldn't be progressive exploration of the program, and it would just become random search. And to a degree, that can be a good thing, right? Random search is great for when you're initially exploring a target, but for testing a target in depth, it is inherently limiting. OK, let's move on. Another problem. What happens if our coverage is lying to us? OK, so first of all, I want to talk about OSS fuzz. I'm sure many of you have heard of OSS fuzz. It's this idea that we can fuzz everything all the time with every single commit, right? And that's the general premise of OSS fuzz. And it works really well. They found 36,000 bugs over the last, I think, 8 years of running. And what's really incredible here is just the sheer number of projects that they're testing, right? Something like 1,250 projects nowadays. And I took this screenshot like 2 months ago, and it's already out of date, right? And let's talk about a particular project in OSS fuzz, libwebp. Some of you already know where this is going. So libwebp has been in OSS fuzz since 2018. So since the very near beginning, they found 43 bugs, and it's very well covered, right? They get 90% coverage from fuzz testing, which means that the fuzz program alone has searched its way through 90% of the code. It's It's pretty incredible stuff. On the other hand, it's also being exploited by mercenaries in the wild. How did this happen? How did we get to a point where our fuzz testing failed us so much? In order to explain that, I'm going to explain what happened in this particular bug. Very hand-wavy. So, to start with, libwebp has a compression algorithm inside of it that allows it to do lossless compression based off of the most frequent sequences observed. This is known as Huffman coding. I'm sure many of you are aware. But what they do is they have a compression table that's stored in the file itself, which is composed of 5 parts. And in order to parse these 5 parts, which are all the same shape, they have a function which reads the whole table in, and that allocates some region for it, and then it calls a subfunction, which then tries to read each part individually. The problem being that in the libwebp case, some particularly experienced researchers who then used it for malicious purposes found a way to extend beyond the length of the original buffer that had been allocated, and thus leading to the 5th component being too long and overshooting the buffer. Yeah, I said that already. Okay, so the reason fuzzers don't find this is, you remember originally we talked about how we're looking at each condition, but that condition doesn't have the context of what part of the data it's reading. So we can guide over this region, but we'll get the same coverage every time. So there's no incentive to actually search for the condition for which we actually overflow this buffer. There's nothing guiding the fuzzer to find this bug. And to quote Marquez here, if there would be a program flow specific to a crash, fuzzers are really good at finding this. But in this case, you would need to be able to guess 20 bytes in a single mutation in order to find this bug. It's 2 to the 160. Not very likely. Okay, and the real takeaway here is that fuzzing is not just some magic thing that just finds bugs and all of them, right? You have to guide the fuzzer with program-specific guidance and look for program-specific blockers that prevent you from finding the bugs in your applications. Okay, and now we get on to the existential dread part of the presentation, which is the ugly, right? We talk about bugs generally, categorically. We say we found this many bugs, but what does it mean, this word bug, right? What exactly are we looking for with fuzzing? So I started out by saying, okay, if the program crashes, great. And this is the general loop that fuzzers use of all varieties, regardless of what their internal machinations look like. So we create some input, we run it on the target, we see if it crashes. If it doesn't crash, we keep going. If it does crash, we emit that crash input to the tester for further analysis. Right? But we don't have to limit ourselves. Right? We can create an input and then take 2 programs which implement the same task and then check if they're different. And if they're not different, we continue the loop. And if they are different, we emit the different input, right? Or the differing input. And this is really cool because it unlocks some new strategies for us, right? We can test for the differences in 2 programs. We can use one program as an oracle for another program. We can check for program properties, right? We can basically look for things like if I have a formatter, right? If I run the formatter multiple times, the output should be the same, right? So if I just take an input, run it twice, I can check if the first and the second outputs are the same. Similarly, I can check for, let's say I have a parser and an unparser, so something that turns the AST into an actual concrete source code. I can check if between parse, unparse, and parse again, that the actual program or the input was treated the same way. Similarly, I can check for things like if I have a real-time operating system and I want to guide towards situations where I'm going to violate some time contract, right? So on and so forth. And these are really good, right? These are very effective things to test for. And I'm sure I don't have to tell you that they show up in unit tests, right? But you can use them in fuzzing as well. The only problem is they're harder to find with fuzzing. but we don't really know why. So this is some folklore research, right? What I found when applying these things is that because they're embedded so deeply in the business logic of these programs, and you're wasting so much time in the parse and validation stages, it's very difficult to find these bugs in practice, right? Fuzzers just aren't equipped to find them. And not all of these crashes even matter, right? What do we even do to determine whether or not two crashes have the same root cause? These are unanswered questions. And I recently encountered this with another regex engine, the pro-compatible regex engine, in which the developer said this: I am not at all sure it is worth trying to find fixes for every one of them. And the reason for this is I found a bug that in order to fix it, you would have to make 1.5x performance losses in order to check for it. And no one would ever find this problem again. Okay, and I talk about this more in depth in the thing that you found me for. And I just want to highlight, you should use fuzzing for these kinds of problems, but be aware that there's going to be difficulties in finding some of these bugs. Okay, and then let's talk about problems that we have in academia right now, right? So I use this picture here because I'm sure all of you will recognize it, but number go up. Basically, let's say I have two fuzzers, like so, and I want to know which one is better. Seemingly a good question to ask, yes? So I can take some benchmarks, which tell me, which are just programs that I know to be fuzzable, and then I take some trials for each fuzzer, and then I run each one of those trials across each of those benchmarks, and then I get some information about the performance of those fuzzers, right? In this case, I'm looking at coverage over time, right? And you can see here, there's a clear winner, right? LibAFL. The only thing is that turns out that these comparisons are actually very misleading. To start with, many academic fuzzing papers that we reviewed did not adhere to the statistical test that we recommend for actually investigating whether or not results are significant in regards to testing between coverage over time gains, right? Similarly, a second paper, not by us, demonstrated that when you rank fuzzers by their ability to find coverage versus their ability to find bugs, this doesn't agree. In other words, fuzzers which are better at finding coverage are not necessarily better at finding bugs, which is a very surprising conclusion. And we're not even hitting the main point here, which is, what are we benchmarking? Does it matter how many lines of code I can cover in 24 hours if I can't find every bug? What are we even measuring, right? If I look for one bug, that doesn't tell me anything about how well I can find another bug. Each bug is qualitative. It's a measurement that is necessarily unique per application. So for these reasons, there are some problems with how we're testing fuzzers nowadays. And I want to urge you to not rely on the results of these as individual global truths to hold, right? When we benchmark fuzzers like this, we're necessarily overfit, right, to the programs that we're trying to test. And not only that, but the majority of fuzzer problems that we actually encounter in practice are program-specific ones. A general-purpose fuzzer is simply not capable of solving problems present in different applications. So where we're needing to go next is looking for applications in fuzzing where we can solve specific program hurdles, solve specific problems in specific programs and specific program classes, rather than just trying to make number go up. And to cap it off here a bit, I want to go back to the quote that I put in the very first part of the slideshow. We're just trying to find bugs. Here's the complete quote. Fuzz testing is not meant to supplant more systematic testing. It is just one tool, albeit an extremely easy one to use in the tester's toolkit. That is to say, don't learn helplessness by applying fuzzing. Right? And to stress this further, Fuzzing does find bugs. It's very good at finding bugs, but it does not prove their absence, right? It doesn't give us a whole sense of what's happening in the program. And to me, this doesn't tell me that fuzzers are good. It tells me that our other testing practices are really not good enough, right? Fuzzing is a litmus test for the presence of latent bugs that you just haven't found yet, right? So obviously I've been pretty critical here. Should you do fuzzing? Yes. Not only should you do fuzzing, but start simple, right? Start with some basic application of fuzzing in order to understand how to interact with your system. Then go forward and investigate the coverage in depth, right? Covering a node in your program doesn't mean you've actually tested it, right? No one should believe that, right? Looking for particular problems in our particular programs, right? What is stopping us from finding new bugs beyond just we can't hit this line of code? And specialize your fuzzers accordingly, right? Building new strategies for your application. The best fuzzer to fuzz your program is the one you built for that program, right? Regularly audit your fuzz harnesses, by which I mean don't let them bit rot. Many OSS fuzz harnesses that we observe in the wild simply are not doing anything anymore because they haven't been updated in 6 years, right? And finally, interactively build and use your fuzzers. Don't view them as something to drop in the CI/CD pipeline and forget about, right? This is something that you as a researcher, you as a quality assurance tester, you as whoever you are, need to be constantly using and updating and investigating how that fuzzer is exploring your program and what exactly is happening. In other words, don't just fuzz. And I want to cap this off by making one point which kind of circles around back to the very first presentation today, which is you'd prevent more bugs by using memory-safe languages and error-safe design patterns than fuzzing ever could find. If you're going to build a system, don't build a massive fuzzing pipeline, just rewrite it in Rust. All right, and with that, I'm going to open for questions.